Good morning, everyone. It is a morning for me here, but I'm thrilled to be here, and many thanks to the conference organizers for giving us the opportunity to share our research here. My name is Renita Murimi, and on behalf of our co-authors, we are going to present our findings about a decade of development of mental models in cybersecurity and what that means for the future of this discipline. So moving on. Cybersecurity is fundamentally a problem of complexity. According to recent statistics, 85% of cybersecurity breaches last year were due to human error. If the human were eliminated, it was found that 19 out of 20 breaches, which is 95% of breaches, could have been eliminated. So this brings into sharp focus the need for understanding why is it that the human element inside cybersecurity leads to so many breaches. Humans have always resorted to mental models to making sense of complex environments. There has been steady research in mental models in different disciplines, and mental models are primarily a way to take elements out of complex environments and simplify them so that humans can move forward with a plan of action for the scenario under hand. So an effective mental model in cybersecurity should keep up with the advances in cybersecurity. It requires a human-centered foundation, and it is very much dependent on the technology, the context, as well as the human behavior itself. All of these are important points to consider because cybersecurity is a field that rapidly changes. So a mental model that was good for Web 1.0 or Web 2.0 might not necessarily be the best mental model for Web 3.0. Similarly, a mental model that works with passwords might not translate well with mental models for firewalls. So the rest of this presentation will look at mental model research in different disciplines within cybersecurity and present some implications for how we can take these lessons and move forward. So moving on. Mental models within cybersecurity can be broadly classified as folk metaphors and formal models. We'll first look at the folk metaphors. And I also wanted to bring your attention to the numbers for references. Please see the full paper for a complete list of references. I've just listed them here for brevity. So folk models are derived from analogies to common social phenomena. These include terms such as the medical model, the warfare model, the infection model, and so on. These are terms that people can easily refer to and make sense of. Versus formal models that is derived from formal engineering disciplines. Now, although we label models as folk models and formal models, this categorization is not absolute because there are some studies whose findings about mental models have significant overlap between the two, and so they do not uniquely fit into any one category. And we have to realize that these categories exist on a continuum, but for simplicity of presentation, we are going to split them into two, folk and formal. So moving on again. Formal models are derived from a range of disciplines. This includes control systems, human factors engineering, and state models. They have terms such as error states and blocking states, which let users move into different states of operation, and then based on a series of foundational if-then constructs move to the next state. If a user moves into a state and is unable to move forward, then it could be that the system has blocked the user, or maybe there is an error that needs resolution. So this is one category of formal models. The next category is one that uses control systems, cognitive security models that use control techniques to model how users behave when they're faced with cybersecurity warnings or advice, or even a set of actions. There are some models, as I mentioned, that straddle the space between two. For example, a work in a different paper modeled cyberspace using a combination of folk and formal models with 3 layers. So the first layer was a technical layer, and then a social technical layer, and finally on top was a governance layer. So all in all, this paper had 11 different models, 3 layers and 8 models. Now, so you see the folk mental models are called crown jewels, kill chain, a triple bow tie model. So examples of folk and formal models are spread across various disciplines and frequently overlap. Moving ahead. Much of what users understand about mental models is through interfaces. When people face a warning about cybersecurity, maybe it's a dialog box that asks them to change their password, or another box that pops up on the side that says a virus has been detected or something has been activated and needs immediate attention. It is the user interface that a user is dealing with. And so mental models depend very heavily on the design of the user interface. For many years, over the past couple of decades, the prevailing notion within cybersecurity was that humans are the weakest link. And taken from a very narrow perspective, this might be true. But we do have to understand that humans are embedded in very complex networks, most of which they do not understand the operation of. And so their processing or their understanding of these different systems and technologies is mainly from the user interface. And that understanding may also be flawed. As we said earlier, a mental model is a way to look at the surrounding environment and extract elements that simplifies the environment to a level that the user can move forward. But mental models are not always accurate, and sometimes they are partial, they're incomplete, or inaccurate. So research over the past few years has been countering the notion that humans are the weakest link. Instead, they're pointing to the reasons why humans are supposedly the weakest link, and those include lack of clarity, uncertainty, as well as expertise. A user's expertise with the particular technology heavily influences how the user thinks about the system and makes prudent decisions about moving forward. And interface design research has now shifted to what is called as human factor integration. So instead of blaming humans as the weakest link and developing security architecture in their absence, how about we integrate humans into the design of cybersecurity systems? Some solutions in this line of research include bringing the user in for development of these interfaces and context-independent guidelines. This might seem counterintuitive. We want context-dependent guidelines. For example, when a user is dealing with, like I mentioned, passwords, or a user is dealing with firewalls, they're very different systems. So we would want context-dependent guidelines, and there is room for that. But context-independent guidelines for interface design for competing or very different technologies makes it easier for the user to take best practices from one subdiscipline and apply it to another without losing too much of the commonalities. Another solution also looks at too many warnings. Do we have too many warnings in cybersecurity? Are we constantly flooded with threat assessments and emails about phishing campaigns, as well as local computer warnings and pop-ups and notifications, not to mention the many notifications on our other smart devices, including cell phones. So it could be that we need effective risk communication that does not put the burden of choosing upon the user, but instead presents the user with a curated list of high priority notifications that the user needs to work upon, and the rest is handled by the computing infrastructure itself. And work at the NIST has also looked at the concept of usable security. Surely the trade-off between usability and functionality has been ongoing within computer science and HCI for a very long time, and usable security simply extends that notion. The next thought about security is that of perceptions. Why do users choose to follow or ignore common computer security advice? And that brings us back to what do people do when they see a security warning? In our paper, we have spoken about this at length, and I'll only briefly allude to it here. When faced with a security warning, people have a few options. First is completely ignore it or weakly engage with it. The third one would be to do exactly what it says. And the final way of engaging with the advice is to do not just what it says, but to go above and beyond. So work in this paper, the first paper highlighted here, looks at why do users choose to follow or ignore common security advice. And they studied this question from 4 different angles. First one was keeping software up to date, using password managers, using two-factor authentication, and changing passwords frequently. And they found that beyond the understanding of technology itself, it was the risk perception. How do users perceive the risks inherent in that technology? And how much do they think those risks will actually impact them? And that was fundamental to their understanding of whether or not to engage with the advice and how deeply to engage with that advice. More work has more work has called for the need for security advocates. A security advocate is very much like a person who does some training and outreach and advocates for the user and explains to the user the trade-offs from using versus not using a certain security feature, or dealing deeply versus dealing very shallowly with certain security advice. I would like to also heavily emphasize that most of the research from about a decade of cybersecurity mental models looks at 2 categories. And these 2 categories are experts versus non-experts. Experts are defined as people who are maybe working in the IT industry or have some computer science experience or a background. And non-experts are mainly classified as home users, people who are primarily end users with no formal experience or background within computer science or cybersecurity. In multiple mental models, too many to mention in this presentation, but enumerated in the paper, have found that, as expected, they have found that experts have more effective mental models than non-experts. Another model of perception of security is the technology threat avoidance theory. It's coming from the information systems background. And it found that non-experts who do not choose to protect themselves think that the threats are not real or not harmful, or that implementing the countermeasures is more expensive or not as effective and maybe just difficult to implement. Another aspect of this theory is that non-experts who choose not to protect themselves using cybersecurity advice simply think that maybe it is not their job to do so. And this is where something like a security advocate would be very helpful to explain how we are all part of networks where problematic activities by even just one account could jeopardize the entire network. So moving on. And in what follows for the rest of this presentation, we are going to highlight mental models in distinct disciplines. These are not comprehensive, but these highlight how people look at different technologies, platforms, types of users, and different applications. So broadly looking at online internet behavior, non-experts had simpler mental models. They do not consider the different levels or hierarchies or the distributed architecture of the internet. And much of it comes down to how much experience do people have with the technology. Mental models are not static. As users become more and more fluent in a particular technology, their understanding of how it works and even the security risks improve. And so in different papers showed that users' technical knowledge influences partly their perception of how to behave safely on the internet. And they also depend, in addition to their experience, they also depend on the cues that they receive from their privacy-related decisions. It is important also to understand that although we broadly lump users as end users are in different categories, and some of them might have a more security experience than others. And therefore, there is a need for software that is able to look at the profile of individual users and tailor security interventions for them. For example, a child user who is using the school-supplied computer or laptop or some kind of a device for schoolwork versus a teenager, and someone else who has been working in cybersecurity versus someone who is completely new to this discipline. The security interventions for these different categories of users will be effective if they are tailored to that type of user. Some other work has looked at using the media. How about using fictional portrayals from TV series, for example, the Bourne movies, which depict a good amount of security risk from online activities, and finding out how users build mental models of cybersecurity risks from watching these movies. What do they understand about security from their observations of incidents portrayed in TV series and movies? And similarly, comic strips too have been used to illustrate some aspects of cybersecurity risk and mental models. Next, we look at more specific disciplines, phishing and firewalls, single sign-on, as well as secure browsing. It was found that because these technologies are more technical than just, let's say, browsing, we found that the findings are mostly related to expertise. Understanding of the technology was important in forming mental models, and therefore the mental models of users who did not quite understand the complexity of the technology were mostly incomplete, partial, or partially correct or complete. There were also cognitive limitations found in passwords. We know that password research has been a robust field over the past decade or so, even stretching further on. And research has focused on what are some limitations on long passwords. Current password guidance says that we need long passwords full of random characters. But as we all know, we cannot effectively remember them, especially when the advice is not to reuse them across different web browsers and applications. So the cognitive limitations of passwords effectively ask for us to use a password manager. But the work in the papers in the third bullet point talk about mismatch of mental model. People quite don't understand how passwords are used. As well as for admins, admins who are more well-versed and have more experience with technology. Their mental models of secure browsing were very different from that of users who did not have that kind of admin level experience. So secure browsing meant something very different to them. And the only way that users could quickly understand the difference between the two was with the padlock sign or the green sign on the browser URL box, which indicates to them that certain websites are more secure than the others. Moving on. Thank you. Now, next we shift our focus to user types. Mental models of cybersecurity have been studied within very specific user types, of which we'll highlight 3, but we'll mention that they've been studied within the elderly population who use the internet, incident responders, ER medicine. And for example, children rely heavily on parents to tell them how to proceed when a box pops up on the screen. And parent strategies at that point were studied. It was found that parents use passive strategies. So they defer to the future and they mostly think that the students or their children will learn about it in the future. Journalists, on the other hand, I attended a very compelling talk by Anjali Sherry yesterday, and she was talking about journalists and cybersecurity attacks within that discipline and what are best practices for them. And some work in this paper has looked at journalists avoiding the use of technology altogether because they're never quite sure about what technology is present in a room when they're gathering sensitive data. And that technology could be something very unobtrusive, like maybe a smart watch or a smart pen. And it might interfere with the privacy as well as security of the data gathering process. We also looked at CIOs, Chief Information Officers, and in that research, it was found that different phases of growth within a company call for different mental models within the CIO's working memory. Moving on. Mental models are coming mainly from an intersection of different fields. It includes cognitive neuroscience as well as human-computer interaction. And social factors play a huge part in how users come up with mental models. Countering the notion once again that humans are the weakest link, a new framework was proposed. It was called the Human Factors Ontology Framework that says that humans are both risk factors as well as risk mitigators. So instead of blaming humans as the weakest link, we are now empowering them by saying that sure, they are risk factors and they are threat vectors, but equipped with the right tools, they can be risk mitigators also. And in that paper, they looked at trust. How do users trust the security advice and deal with the context around them and coming up with mental models? And this context could be a combination of their own experience, their inherent experience, as well as context-dependent experience. Privacy and security have also been studied as factors in developing effective mental models. And some work that is directly related to the GDPR was studied in the paper highlighted here. And the specific domain studied here was medical data sharing. So moving on. Next, we look at mental models of encryption and machine learning. Encryption in particular has been brought to the forefront with a lot of new technologies in Web3 that we'll look at soon. But passwords, for example, are heavily dependent on lots of cryptographic primitives, including encryption. And the mental models that were found to be used in among users were that of access control. A password is used for access control, or for some users, a password technology just looked like a black box. They knew that they entered a password and they did not quite know how the password gave them access to a particular system like their email. And so it functioned very much like a black box. Others with more experience understood that it was a cipher, so it takes some plain text and produces encrypted text. And more advanced users understood that password encryption proceeded in rounds. So while they were not entirely sure of how many rounds, 16, 32, or 54, or however many, they did know that it was rounds and rounds of encryption in different levels. And so the findings of that paper called for the need for better communication to inform users how passwords worked at a level that they could comprehend. And another application also looked at encrypted communication links. Why would users choose, for example, a mobile communication app that was encrypted versus one that was not encrypted? And they found that security and privacy were two important factors in coming up with that decision. The security of machine learning systems is also important. It mainly was dependent on how much expertise a user had with the machine learning system, and it was grouped into the structural and functional components of the system. So users knew that if they were developing algorithms or they were developing the interfaces for these machine learning systems, they were dealing with different potential vectors for threats that matched the machine learning system. Moving on. Mental models of smart homes, Internet of Things devices, as well as cryptocurrencies were our next focus. Mostly it was found that users' understanding of smart homes was superficial. In another paper that we recently published, we found a statistic that said smart homes are vulnerable to attacks at the rate of some homes experiencing thousands of attacks within a single week. And users' understanding of smart homes was mostly superficial. They knew that they would connect a device to their home network. And beyond that, there was not much activity done on the part of the user. And the device would mostly slip into the background, and there would be no active security work being done for the device on behalf of the user or the manufacturer. Users also developed mental models depending on how they saw the device being advertised in social media. And a big part of how users dealt with these devices was based on their own errors and biases. They might base their understanding of these IoT devices on how they interacted with the non-IoT version of them. So for example, if I have a toothbrush versus a smart toothbrush, a light bulb versus a smart light bulb, and they base their understanding of the functioning of these devices based on how these devices operated without internet connectivity and without computing power. So users' own errors and biases impacted a great deal on their mental models. The next thing that we found was cryptocurrencies. Most users had major misconceptions related to how cryptocurrencies worked and who managed the keys, and most of their mental models were incomplete or inaccurate. And because the overwhelming majority of users had incomplete and inaccurate models, there is a need to have encryption by default, because cryptocurrencies and most blockchain-based technologies depend very heavily on the management of private keys. And the terms and conditions of most of these applications ask for users to maintain their keys securely. So security of keys is the responsibility of users, and therefore the need to have encryption by default is the finding of this particular line of work. Moving on. So that brings us to almost the end of our investigation into mental models. We think that in the future we need standardization efforts, and we say this very cautiously because mental models are not static and they're not uniform. We understand that there might be two users who everything else alike understand the technology to the same level or have the same amount of expertise and training, but they might have different mental models of their technology. So we're not calling for standardization in terms of mental models because we cannot control that. But surely we can curate a database similar to the CBE database of different mental models so that users with different levels of understanding can look at a mental model and come to a better understanding of the technology itself. Similarly, a database such as this, a curated database such as this can help designers of interfaces, and they can then develop tailored interfaces that change in response to context of operation of the technology. We're also calling for the need for social factors. The development of a certain technology in a particular country or in a region might not benefit users in a very different sociocultural background. It also calls for linguistic interpretation of cybersecurity advice. Certain metaphors in a region might not resonate well with metaphors in a different region. And also experience with the artifact. We might have a population that is very tech savvy. We might have a population that's just getting onto the internet. And so social factors are also very important in the development of mental models. And something that's ongoing and will require more effort from a consortium of industry, academia, and government would be the workforce development, a requirement for people who understand how important cybersecurity is to everyday life, even if users are not within computer science or IT. And some work has already been done, as highlighted in the paper mentioned here. They found that cybersecurity workforce development calls for people who are team players, who can understand the need for technical and social skills, as well as a sense of civic duty, because as we mentioned earlier, compromising actions on behalf of one individual can jeopardize entire networks. We're also seeing rapid growth in what we call as Web3 blockchain-enabled technologies. And these will, of course, warrant new mental models because the threats are different. The technology is very new, although it does interface significantly with Web 2, the underlying framework of blockchain is something that requires more outreach as well as education on part of users. Moving on. In conclusion, like I mentioned at the very beginning, when presented with a security warning or a notification, users may choose to ignore it, weakly engage with it, exactly engage with it, or do more than what is expected. So they have different levels and intensities of interacting with the advice or the measure that pops up on their screen. And mental models are diverse. We looked at a good number of papers in many different disciplines. And there is a combination of folk and formal models, models that are specific to disciplines, and no single mental model can claim to be efficient or effective for the entire discipline, but it is also heavily dependent on the context, and they have to keep up with newer technologies. And most of all, the development of security measures has to be driven by inputs from many different stakeholders. It is important to consider end users, vendors, different profiles of users in developing security measures, because each category of users comes up with their own kind of mental models to deal with security. And this concludes our paper, and we'll be happy to take any questions.